Okay, with units 7.5 and 7.6, we're going to look a little more into the equilibrium constant K. And we are revisiting this, K greater than 1, K less than 1. We can call that also, I guess, K very large compared to K very small. And graphically, this is what we've been talking about already. I don't think I showed this to you graphically, but so if K is small, yeah, less than 1, but I think I made it a little more extreme than that, 10 to the negative third. That's an arbitrary cutoff, but at a very small K, not many reactants are going to become products. Most of the products would become reactants, and so at the end of the day, if you were observing this beaker, you would see lots of reactants. Over here, K is large. I just said greater than 1 here, but I made it a little more extreme. And again, these are not really cutoffs. 10 to the third is not, that's just an arbitrary cutoff. But at large Ks, almost all of the reactants become products. Now, we'll quantify this as we get further in Unit 7. We're not quite ready to do that yet. But at the end of the day, again, K being large, you're going to be able to observe lots of products formed. And then you have all this in-between area. And again, these numbers are arbitrary, 10 to the negative third to 10 to the third. But in this, you're more of a true, I think what most people can kind of consider an equilibrium system, where you're going to have lots of reactants and lots of products in the beaker at the same time. This is our first introduction into this table here, but this is going to be really useful, and we've used this actually a little bit in stoichiometry. Let's change this color a little bit here. I used these rows and columns. So here's a chemical reaction. H2 plus F2 making 2HF. And initially, you have a certain amount of material. Now, with stoichiometry, we were using moles typically, but it's going to be, I think, more to our advantage to keep these in molarities with equilibrium. And as we move forward, I think that'll become evident why we like molarities. And then the second row here is change. What are you going to lose? What are you going to gain? And since we're starting off with 2 molarities of reactants and 0 products, there's no way else it could go other than proceeding reactant to product. So we're going to have some negatives with the reactant side, some positives with the product side. And if you notice, with this K being large, at the final concentration, and we're going to actually change that final to the word equilibrium. So these are going to be called ICE tables. You're going to notice that almost all of the reactant gets used up. But it's not a completion reaction, it's an equilibrium. So most, but not all of the reactant gets used up. And we'll figure out how to quantify this a little bit later. We're not quite ready to do that yet, but I just wanted to show you that most of the reactant gets used up, and then we make a tremendous amount of product. So if the Ks are large, these changes in concentration are significant. What I mean by that is they have a significant effect on the initial amounts, as opposed to if the Ks are small. And if the Ks are small, that's approximation. That's what that stands for. It means it's virtually 0. Not 0, but virtually 0. That's the actual number in this particular reaction for the change. But if you get on your calculator and you do 2 minus 2.00 times 10 to the negative 6th, and by the way, it would be that number in the change row for H2 here, like I wrote, because it's a 1. Whoops, nope, it wouldn't be 2, sorry. It would be 1 because it's a 1 to 2 ratio. So luckily I caught that there. But anyhow, 2 minus 1 times 10 to the negative 6 molar is going to get you on your calculator basically 2. Now, yes, you are losing a little bit of that 2 molar, but an infinitely small amount of that. So close that we can say it's approaching 2. And you can only do that if the K's are small. Okay? And how do you know if the K's are small or big? Well, wait until you're done. And we don't know how to do these calculations yet, but once we learn how to do these calculations, if the final amount has an impact on 2, then I don't think we're going to kind of define that as very small anymore. And as we get more, as we get deeper into these questions, I think you'll get a better feel for when it's very large or when it's very small. So here's a couple of questions that at least gets you introduced to this idea. So we have a K of 14.5 for this particular reaction. Okay, and I'm going to have to move this up a little bit so we can see the question. Of course, we already have the answer, so we know it's going to be answer B. But let's go and actually work on this ICE table idea that we just introduced. So ICE. Now we used to call it F, ICF, but we're going to call it ICE now. We have 1 moles of both reactants, and it's in a 2-liter container. So 1 mole divided by 2 liters is 0.5 molar. So let's put a 0.5 molar in there, and let's put a 0.5 molar in there. And that's what our initial amounts are. 14.5 is greater than 1. So we think these might have an impact. They're significant. Now, I don't know if we're going to be able to tackle that yet, but these values that we're going to put for the change are going to be important. Now, with that last slide, we had numbers. Well, we don't have numbers here. So in math class, when you don't have numbers, you use variables. So the variables have to, in this change row, have to match up with those coefficients in the balanced chemical equation. So an X, a 2X, and an X. So it's going to be 0.5 molar minus X, 0.5 molar minus 2X, and 0 plus X is X. Now, we'll figure out how to do that mathematically in a little bit here, but I think we have enough information to be able to tackle this answer. Which of the following is true at equilibrium? So equilibrium is this row right here. So what's going to happen? So is CO and H2 going to be the same numbers? Well, you can see here they're not the same numbers. 0.5 minus X is not the same thing as 0.5 minus 2X. So I think that's how we're going to be able to get to that answer B. By the way, lots of people would like to say, oh, equilibrium, everything has to be equal. No, that's not the case. Remember that equilibrium, dynamic equilibrium just means that the forward and reverse reactions are still taking place. Just that at the end of the day, you might have more reactants or more products depending on what the K values are. Okay, so the other thing we're going to be able to do with this is if we know a K for a particular reaction and we have another reaction that has some similarities with it, we can adapt that K as needed. Now there's a big misprint there. Let's change that to an S. So anyhow, if we have a K, we can sometimes raise it to a power. We can inverse it if necessary to match up with this new reaction. Like for instance, if we had, let's go back to the last one so I don't have to write out another reaction here. So if we have the CO plus 2H2 going to CH3OH, what would happen if we had CH3OH going to CO plus 2H2? Well, that K is going to be related to this reaction's K. It's just that instead of it being K, it's going to be 1 divided by K, the inverse. Why? Because we just flipped the reaction on its head there, and we made the reactants products and the products reactants. So let's give one of these a shot. Actually, I guess 3 of these a shot. So we have a reaction that has a K value of 7.07. Well, how is this reaction like the reaction in red? Well, it looked like to me that it's just opposite. So all we have to do is do the inverse of our K, and that would be the answer. Now you guys can put that in your calculator and get an answer for that. How is this second reaction like the one in red? Well, it looks to me like it is just doubled. Like the coefficients, this was multiplied by 2, this was multiplied by 2, and that was multiplied by 2 to get the reaction. So that means any multiplication, basically what we did was we changed these coefficients, so we have to change the coefficients in the K, and remember that coefficients become raised powers, so that would mean that we'd have to do that. And that would be our answer. What do we got with this one? This one is the inverse of the last one. So it would be that. Okay. I think those are fairly easy for you guys to figure out. We're going to use that same idea here with maybe also system of equations, like Hess's law, I guess, where we saw where we saw system of equations. And 2 S's, we need to get to 2 S's. 2 O's and another O make 3 O2s. 2 O2s plus an O2 make 3 O2s. And then 2 SO3s, there we go. And then those would cancel if we combine all these. Now, yes, there's positives in between the 2 reactants, but if we would combine these and put them into a K expression, there's no additions and subtractions there. There's multiplications and divisions. So we can kind of keep that idea in our head there for if we try to combine these K's. So it would be 2 times 10 to the 105 times that. The reason, again, it's not adding is because when we take these reactants and products and we combine them into a equilibrium expression, those are all multiplication and divisions. So the K's would have to be like that also. And we didn't have to do anything to either of these reactions, so we didn't have to do anything with these individual K's. 2 times 7, 1.4 or 14, and then 10 to the 105 and 10 to the 24th would get you 10 to the 129, but remember that I already flipped that from 14 down to 1.4, so we have to also reflect that here. Yeah, so let me show you what I had done there. So 14 times 10 to the 129 is the same thing as 1.4 times 10 to the 130, and the reason I kept it like that because that's how typically you would see scientific notation. And what does that match up best with? Well, we already have the answers, but that matches up with 1 times 10 to the 130. And do we have anything else left here? We have one more. So here we have our reaction, and then we want this reaction. By the way, the K value for that is 95. So how is the reaction that has a K value of 95 like the one we have? Well, it's the inverse, and it's also looked like all the coefficients we have to multiply by 2. And yep, we have an answer. So there's our all our coefficient items multiplied by power 2. And then the inverse is reflected there. Okay, that's it, guys.